All right, so in chapter 4, section 2, we're talking about natural exponential functions. And so when we're talking about natural, that just means we're dealing with something that has a base e. And so in the text, they'll talk about natural exponential functions. So just something that has an e in it. And they talk about some of the good functions, like here's one on number 1, it has e raised to some power versus like a 3 raised to some power. E's just a number, it's like pi 2.7, 1828. 1828, it's got a whole bunch of, it goes on forever like pi. And they have some of these other functions that use a natural exponential function. And so this is a logistic function. I always like to think of logistic functions is something that occurs in nature, like if you start off with two bunnies, a male and a female, and then they do what bunnies do, but eventually they're going to level out because of their environment, how much space they have. You know, you only can have so many bunnies in a specified area. It's kind of like deer population or anything else like that. So we have these logistic growth models, but it's has a natural exponential function in it. When it comes to solving some of these, they also talk about compounding interest. So we could look at some of these equations, these compound interest equations, to figure out what the rate is on problems. But one thing that I want you to be aware of is sometimes we can manipulate Desmos to help us out. So I'm going to look at one of these to give a example. And so if I was doing this one, how much should be deposited in an account paying 6.2% interest compounded monthly in order to have a balance of blah 3 years from now? So if we have that formula, let's reference that formula again because I've already forgotten it. The total amount that you have after a period of time is your principal amount times the quantity 1 plus your rate over n, the number of times that it's compounded. And a year times the number of times it's totally compounded. So I would say this would be like an n times t up top. And if we look at that, I could use that total amount that we have equals your present day value. That's what we're trying to figure out, right? We're trying to figure out how much we have initially. 1 plus your rate is 6.2% divided by compounded monthly raised to the 12 times how many years, and it's 3, so that would be a total of 36 up top. I could look at this, I could add a slider to figure out how much I would have to have, but basically I want to know when this thing, this equation, is equal to, well, let's call this an x. When is it equal to this line of 36,717 and 29 cents? So here I have a horizontal line. Here it has an equation that's going up to that horizontal line. So hopefully where they intersect will be about 30,500 because that would solve for my x value. Let's see if we can make that happen. I know that my x is dollar amounts, and I know if I end at 36,000, well, that means I start with less than that. So maybe we could go from 0 to 40,000. And y, well, here it's going all the way up. This is the total amount that I have. So let's go from 0 to 40,000 as well. So make it kind of square. And we see that there is an intersection, right? So here's my equation of my exponential equation, and here's what I want it to equal, this 36,717. And if I round that, I get 30,500. So that's going to get me to this 36,717.29. So I used Desmos to solve. I could have just computed this and divided it to the other side if this other side was 36,717, but this would be another way of solving this type problem. If I want to know how many years, like if this was an x, that's what we're getting ready to get into. You will have to solve some, but we're going to start taking the derivatives and find the slopes of particular values. But that's where in previous classes you've done logarithmic equations to help you solve those. So today we just have exploring some of these exponential equations to solve. So hopefully this will help for Chapter 4, Section 2.